Hi, Mishal here. This is the second video in the series of algorithm tutorials. In this video, we are going to talk about the asymptotic notations. Generally, the asymptotic notations used to represent the running time of an algorithm, as the time complexity is the major case of concern. So there are three notations that we use to define the time complexity. First is big O notation, second is big omega notation, and third is theta notation. It basically represents upper bound, lower bound. Now let's consider the big O notation. Big O notation. Consider a graph. This is your time, this is your number of inputs or data or n, whatever you say. Along with the data, the time required by your function increases, represented as f of n. Now, if we had another function that takes more time than this function, then that takes more time than f of n, then we can say that f of n is less than or equal to g of n, and f of n could be big O of g of n. This is what big O notation says. But there are certain conditions that we will be looking forward. But first of all, let's take an example for this. Consider, let me make it over here, f of n equal to n square and g of n equal to 2 raised to n. For n equal to 1, n square would be 1 and g of n would be 2. N equal to 2, 4 and 2, n equal to 3, 9 and 8, n equal to 4, 16 and 16, n equal to 5, that is 25 and 32, n equal to 6, that is 36 and 64. Now let us analyze these 6 points. Now first of all, what we can say about f of n in relation with g of n. Obviously g of n is greater than f of n. What can we say about this thing? Again, f of n would be greater over here. What over here? Again f of n would be greater. Sorry, my mistake, 4. It would be equal, not the greater. Again equal. G of n. So what we can say that from n is equal to 4, f of n is equal to big O of g of n. This is what we can say. But when n is greater than or equal to 4, or n naught is equal to 4 or greater. So what is n naught over here? Is this point n naught. Let us look at the second point. That is big omega. Again the same thing. Time, data. Now what we are supposed to do that? If your function output time increases with the number of data, consider it as f of n. Now thing is reverse. If we get a function that is less than f of n, then we can say that f of n is greater than or equal to g of n, and f of n is equal to omega of g of n, big omega of g of n. Okay. The same example what we did in the previous one. F of n equal to 2 raised to n, g of n equal to n square. Now this is your g of n, this is your f of 1. Now what we are supposed to do that? Finding the relation. Here f of n is greater, here both are equal, here g of n is greater, here both are equal, here f of n means there is again f of f. So from this point n equal to 4 and not, we can say that this condition is satisfied or if and only if n is greater than or equal to 4, then this condition is satisfied for the given particular problem. Last but not the least, that is theta notation. Theta notation, very simple, the mixture of both the notations. If you have f of n time data, what it says that C1 and C2 g of n, what it says that if you get the two values of g of n such that f of n is in the center, this condition has to be satisfied. This condition has to be satisfied. Means that for a given value of g of n, by just multiplying the c1 and c2, two different numbers, we get a function such that the second part, that is multiplied by c2, is less than f of n, and the first part, that is multiplied by c1, is greater than f of n. That's it.